In this course, we are going to talk about computational social choice. And I'm particularly surprised that so many of you show up, because I guess many of you have no idea what computational social choice is. So at least it seems like it sounds interesting. So computational social choice is like the merger of two different things. So it's first social choice theory, which is about 60 years old. So in 1951, there was a very influential paper and book by Kenneth Arrow, a Nobel Prize laureate, who proved a very famous impossibility theorem called Arrow's impossibility. Who has heard about this result before? Okay, some have. So of course we are going to study this result in detail, and this essentially kickstarted the entire area of social choice theory, which is about the aggregation of preferences. So I'm going to talk about this in more detail later, of course. And then more recently, so about 15 or 16 years ago, computer scientists became interested in social choice theory, and that is what started the area of computational social choice. Because in social choice theory, the properties of many aggregation functions have been studied, but things like computational complexity or compact representation of preferences were not considered by economists and political scientists, and therefore computer scientists had a lot to bring to the table and enrich the discipline of social choice theory. And that is what computational social choice is about. In the lecture today, which will be quite different from the following lectures, I'm trying to give you a very broad overview of computational social choice. I will touch many different things just a little bit to hopefully show you at least something that gets you excited. So if there's something in here today that you find interesting, then you should come back next week, because I know that, well, probably not all of you are going to come back next week, or maybe 2 weeks or 3 weeks from now. Even if not, you may want to stay tuned, because there are some quite exciting topics coming up later on. Okay, so as I said, so many of you probably don't even know what social choice theory is. Well, the name gives it away a little bit. So, well, there's no like clear-cut definition of social choice theory, but the main question that we study in this course is how to aggregate the possibly conflicting preferences of some agents into collective choices. And then it says on the slide here, in a fair and satisfactory way. So of course these terms have been not defined. So if you are like more into formal things, then don't worry, because later on in the course everything will be formally defined. At this point, it's just a bit blurry, and we are just saying that these preferences of the agents should be aggregated by like satisfying desirable and intuitive properties. So this area originated from mathematics, economics, and political science. So it by itself is already interdisciplinary. And then we are adding computer science on top of it. So it will be highly interdisciplinary. So in general, I would say that this course is, well, all the courses are different, but I think this course is really very different from all the other courses you have attended, because it's really a unique combination of topics from mathematics, computer science, economics, some concepts from political science. Yeah, it's a quite unique combination there. And the essential ingredients that we study, or that all these social choice problems have in common, is that we have some group of autonomous agents. So these agents could be humans, for instance. If you have a human election, like a Bundestagswahl, for instance, then it's pretty obvious what social choice theory is about. So we have a voting rule that aggregates the preferences of the individual voters into a winning candidate, for instance, or winning party, or seat assignment for the parliament. So in this course, well, the agents don't have to be humans. It could also be programs or robots. It doesn't really matter. So we will just talk about agents. So this is a term that is common in economics, which just means that it's an individual decision maker which is autonomous. Okay, so we cannot really influence what the agents are doing, because they are autonomous entities. Then there's some set of alternatives. So in this course, we will only be concerned with finite sets of alternatives. So these alternatives could be like candidates running for election, which is the prime example for social choice, but it could be many other things as well. So it could, for instance, be that, for instance, we as a group of people are deciding on a plan to pursue. So then it's like maybe 100 different plans that we can choose from, and then we have preferences about these, and then we want to collectively decide which plan we are following for the rest of the semester, for instance. And then these agents have preferences over these alternatives. Again, we are going to formally define them next week. So you will see some examples today where this is going to. Preferences could be many different things. So it could be that we have a set of alternatives that we like. It could be that we can rank order all the alternatives. It could be that we assign utility numbers to the different alternatives. where in social choice this is usually not considered because it's a bit unclear what these numbers actually mean, in particular if we're comparing these numbers from two different individuals. So if I say alternative A is like 10 and another one says alternative A is 17, so it's not really clear how to compare these kinds of numbers across individuals. Therefore, in social choice, usually preferences are assumed to be purely ordinal. This is in contrast to algorithmic game theory, for instance, which I guess some of you have taken. So who has taken algorithmic game theory? Okay, so I didn't read it last semester because I was on sabbatical, but I'm going to read it again in the summer semester. In algorithmic game theory, we usually assume utility functions. Here, preferences are just, in most cases, just ordinal preferences where we are able to rank order the alternatives for any given voter. And then there are aggregation functions. Again, aggregation functions is a term that captures many different things. So, for instance, we could have a function that aggregates these preferences into a unique alternative. So we want to find the best alternative according to the preferences of the agents. In some cases, it will turn out that we cannot really find a best alternative, but only a set of good alternatives. So the outcome of this function, as we are going to define it, could be a singleton or it could be a set of alternatives. So these kinds of functions are called social choice functions. In some cases, we will also study social welfare functions, where the outcome is a ranking of the alternatives. So this is quite natural in society. So we have individual rankings. So like each of us could have a ranking over the possible alternatives. And then we have a function that aggregates all these rankings into a collective ranking of the alternatives. Okay, and then yet again, at the end of the semester, we are going to study functions where the outcome will be, for instance, a lottery over the different alternatives. So a probability distribution. So lotteries is usually what economists call a probability distribution. So just a probability distribution over different alternatives, where we, for instance, say that it's that we probabilistically pick an alternative based on the preferences of the voters. So as you can see at the bottom of the slide, so this very general framework that I just sketched has lots of applications. Like the prime application usually is voting. So when people think about social choice, they usually think about voting, but there are many other applications as well. For instance, maybe let me pick out one or two of them. So for instance, here it's also mentioned that, for instance, matching or coalition formation can be considered a special case of voting. So at TUM, for instance, we have this matching system that matches students to courses. Okay, so here you can consider this a special case of the social choice problem, because if you define the set of alternatives to be all possible matchings, so all possible configurations of students assigned to different courses, then students, of course, have preferences over these alternatives. We usually assume that students are indifferent, so they don't really care about the assignments of the other students. So they have a ranking of the courses that they like, and then they are indifferent between all the different matchings in which they are assigned to the same course. Okay, so they have preferences over the alternatives, and then in the end, an aggregation function should yield a matching that is good in some sense. Okay, so that's why this is a special case. Maybe another example. Search engine aggregation, because maybe that's a bit more unusual. So there are many different search engines, so like Google, Bing, and I don't know if Yahoo search still exists, but so many different search engines are there. And you can consider these rankings that these search engines return as preferences over websites for a given search term. Okay, you enter a certain search term, and then each of these websites gives a ranking of different websites which they think is most appropriate for the given search term. And then you could want to write a meta search engine which takes all of these rankings from, say, like Google, Bing, and Yahoo, 3 different search engines, and generates a meta search ranking which just combines all these 3 rankings into one ranking. Okay, and we are going to study functions which do exactly this, not for the particular application of search engine aggregation, but which take rankings and aggregate those into a single ranking. So this is a bit of an unusual application, because here the voters would be the search engines, and in particular there would be few voters or few agents and many alternatives, because, well, basically that's the set of all websites. Whereas, for instance, in the voting applications, it's exactly the other way around. So there are usually many voters and only few alternatives or few candidates that stand for election. Okay, but in any case, in this course, we will be concerned with the foundation and theory of computational social choice. We are not going to spend much time talking about particular applications, not even political elections, which is the prime example in social choice. We are really going to study the foundation of social choice theory by mathematically analyzing what is possible, what is impossible, and which properties can be satisfied simultaneously. If you're interested in some of these applications, we are also offering seminars. For instance, next semester there's a seminar called Economics and Computation, and there are some of these things like fair division, for instance, are studied in more detail. But in this course, it's really like the basics of social choice. Okay, so what are the goals of this course and which kind of methodology are we using? First, regarding the goals, so some of the key questions that we would like to answer during this semester. So we are going to start all the way back with a single individual. So while in general this course is about the decisions of many agents, so we will have many agents that have preferences, for the first lecture next week, so the second lecture will exclusively focus on individual decision making because before we start about collective decision making, we need to understand individual decision making. And in this lecture, we are going to define concepts like rationality, rationalizable relations, and consistent choices. For instance, as you can imagine, there could be some mathematical formalizations of the notion that one decision is consistent with another decision, whereas maybe for other pairs of decisions, this is not possible. So this is what we are going to focus on in the second lecture next week. Then once we start to talk about social choice, we are going to define so-called axioms. So the so-called axiomatic method is extremely important in social choice. So we are going to define properties that a social choice function, you can think of these as voting rules for now, should satisfy. Okay, so as you can imagine, so there are some basic properties that seem like any social choice function should satisfy those. So we are going, and this is also what we are going today, we are looking at some social choice functions and check which of these properties are satisfied and which ones are not. And then it will turn out that some of these properties cannot be satisfied simultaneously. And there are some really striking and surprising results in social choice theory. I mentioned Arrow's impossibility already, which show that like you take a collection of maybe 3 or 4 properties, and then you show that no social choice function satisfies these properties at the same time, even though each of these individual properties seems very mild and innocent. So these kinds of results are called impossibility theorems. And these define the boundaries of what can be achieved, and that's why they are so important. Like the most exciting results in social choice are so-called complete characterizations, where we take a bunch of axioms that a social choice function should satisfy, and then we prove not only that there exist social choice functions that satisfy all of these properties at the same time, but that there exists exactly one social choice function that satisfies these properties. And there are some pretty nice results in social choice where you take like a bunch of properties, 2, 3, 4 properties, and then you can prove that there's exactly one function that satisfies these properties. Okay, next bullet is about computation. Because as I said, so economists and political scientists didn't pay much attention to computational properties. So this is almost a bit amusing if you look at the early literature on social choice. So there are sometimes remarks regarding the computational complexity, but of course these people didn't have the framework of computational complexity at their hand. Okay, so in some cases we can show that some of these aggregation procedures are difficult to compute. In some other cases we are going to identify clever algorithms for identifying winners, which is also quite nice. One other question that we are going to study is what happens if voters can be insincere about their preferences? Because the basic assumption that we had so far is that we have a function that takes as input the preferences of all the voters or all the agents. But of course, in reality, we cannot know what the actual preferences of these people are. Right? So if you have preferences over certain things, but I cannot see those preferences, so they are just in your head. You have to tell me about this. I have to ask you about the preferences. And then it turns out, and we will see some phenomena like this in today's lecture, that in many cases you're actually better off by lying about your preferences than stating them truthfully. Okay, if you know what the procedure is that is being used to select a winner, in many cases, and you also have some understanding of what the preferences of the others are, and probably many of you have done this already in some political elections, if you have this information, then you are best off not voting truthfully. And for the last 2 or 3 lectures, we are going to study this particular phenomenon, where we study in which sense can agents actually improve the outcome by lying about their preferences. Okay, so all of these questions we are going to address using mathematics. So maybe some of you have seen this disclaimer on the homepage where we say that this is a theory course and you should know mathematics. So because we are using mathematics, you need to be familiar with some basic concepts and proof techniques. So depending on your background, this may be a burden for you, and maybe in some other cases it's just not a big deal, because here I'm mentioning some concepts. So it's not really that we need a lot of higher mathematics or something. It's you need to be familiar with sets and relations, because preferences are usually modeled as relations. Directed graphs, as we are going to see, will play an important role. And maybe some other concepts from logic, for instance, that you have also seen in discrete structures. There are 2 documents that we are linked on the homepage, because a common question is where can we learn about the mathematics that is required for this course. So there are 2 documents that I didn't write myself. They are from other researchers, which summarizes basic theory of sets and relations and things like this. So this hopefully gives a better overview of what is required. Today's lecture is really quite different from the other lectures, because in today's lecture, so if you are a mathematician, you might be a bit disappointed in today's lecture, because I'm not going to formally define anything. As I said, I'm going to give you a very broad overview. That's why I'm sketching many different concepts, not giving mathematical definitions, but from next week on, everything will be really foolproof and mathematically defined. So here, there's some literature that is, well, maybe not really recommended. So first comment here is that in order to follow this course, you don't need to buy any books. You don't need to download any books. So all you need is just the lecture slides, the exercise sheets. You need to go to the tutorials. Everything else is just on top of that. So it's mostly for people who maybe want to see a different perspective. Like different people explain things differently. Maybe you don't like my style of explaining things, or you want to look up a definition somewhere else. Then there's lots of books on social choice theory. And here are some examples. And I also noted which chapters are relevant from these kinds of books. So these are all introductory texts. This is also on the webpage. And then there are some advanced books, which includes the Handbook of Computational Social Choice, which is a book that I co-edited some years ago, six years ago in 2016 with some colleagues. So that sounds like it's probably exactly what we are doing in this course, but it's not really like that. So this book contains many things that we are not doing in this course, and we are doing many things in this course in much greater detail than it's covered in this book. But nevertheless, you may have a look, especially since the PDF is for free. So whenever I have something underlined here, it's a hyperlink, and you can just click on it, and then you can see the PDF, for instance, of this book here. Why are there different voting rules at all? Right? So what's wrong with plurality, which is the most well-known and most widespread voting rule in practice? Plurality means that every voter can just name his or her most preferred alternative, and the alternative which is ranked first most times is then selected. Okay, there could also be ties in some rare cases, but this is like the simplest voting rule you could imagine. It's being used in almost all places. And if this is like, it seems like it's a good rule because it's used in the practice a lot. So you may ask yourself, so why can we have an entire course devoted to voting rules? So as it turns out, there are many things wrong with plurality rule, and this is probably the first thing that I want to convince you of during this very first lecture. And to visualize this, I would like to use an example that was given in an article by 2 Nobel Prize laureates in economics, so Eric Meskin and Amartya Sen, published an article in the New York Times. So that was already also 6 years ago. So when Donald Trump won the election, in particular, this is about the primary election in the United States. So before there's the real presidential election, there are primary elections by the Democrats and the Republicans. And in the Republican Party in the United States, Trump was won this primary election. Therefore, he was the candidate for the Republican Party. This just serves an example to see what can go wrong with plurality. So it's not specific to US primary elections or US elections in general. So it happens all the time with plurality. So it's a difficult word to pronounce. So let me show you what this example is about. So it's So in these primary elections, there were also other candidates than Trump. So for instance, in some states, there was Ted Cruz and John Kasich, two other Republican politicians. And in many states, Trump emerged as the winner in this particular state without having an absolute majority. Okay, so like in this example here, so there are these three candidates. 40% think Trump is the best candidate, and 35% think Cruz is the best candidate, and only 25% think that Kasich is the best candidate. Okay, so then Trump emerged as the winner, even though he doesn't exceed this 50% threshold. But that's perfectly fine. If you have many candidates, you cannot expect that there's a candidate that exceeds 50%. In some states, it was in reality even like, I think, 33% for Trump in Arkansas, for instance. So he only had 33% of the votes, but still he won in Arkansas because there were a couple of other candidates. Okay, and then what these two authors did is that first, you can look at these preferences like this. Okay, so there's 40% who think Trump is the best, 35% who think Cruz is the best, and so on. But here you can already see the main restriction of plurality. So you hopefully agree that it's safe to assume that each of these voters who took part in this election not only has a first preference. Right? Usually these voters, so they know all these three candidates, it's not that they only think that this candidate is best, but they also have preferences about the other voters. The other candidates, I'm sorry. They surmised that the preferences in this fictitious state could have looked like this. That 40% of the voters think Trump is the best, then they like John Kasich the second best, and Ted Cruz the worst. And for instance, these 35% of voters here like Cruz the best, and then Kasich, and then Trump the least. And these here, Kasich the best, and then Cruz, and then Trump. Okay, so this is just, nobody knows what the preferences of the voters actually were, and they could have been different from this, but in general, so these people know this topic quite well, so maybe some small fractions of percent were different here, but it doesn't really matter that much. It could be that the general picture looked a little bit like this. And here you can already see that one problem of plurality is that it only takes into account the top choices. Okay, so plurality only takes into account this part of information, but it completely ignores all the other information. Now, maybe so you've seen this thing probably for the first time. If you look at it for a while, so this thing here is what we are calling a preference profile in social choice. So all these 100% of voters, we have split up into groups of voters who have the same preferences. So selecting Donald Trump based on these preferences here seems a bit weird, right? So any ideas of why this might not be a good choice if the preferences are exactly like shown here? Yes?
Of course, there's the second, if the voters for Cruz and Kasich are joined, they have a majority over Trump, but if they're divided, the Trump wins.
Okay. So the point was is that if the voters who like Kasich and Cruz the best, if they merge, if they join somehow, if these two candidates could be joined, then there would be a majority in favor of this merged candidate. That's true? Yes?
I think there's also a majority for people who don't want Trump as president, right?
That's also a good point, right? So if you just look at these last two columns here, so a majority, that's 60% of the voters think that Trump is the worst candidate. So that really seems counterintuitive. You had the same point? Oh, okay.
Because if we take into account all the preferences of everyone, on average, Trump is not the best range candidate, and it's actually Kasich.
Okay. Another good point. So that is so it's if you look at the average ranks here, it seems like Trump is not doing very well. So maybe it's not completely obvious at first sight, but you can compute something like the average rank for all the different candidates, and then Trump should not be selected. Yes?
It encourages voters to categorically lie about the preference because the state that they don't want Trump, so and knowing that their candidate is the weakest, it would be preferable for them to not vote according to their preference.
Perfect. So many different aspects of social choice that we are going to study are being highlighted now. So the comment is that it seems like if voters can lie about their preferences, as I mentioned earlier, then these voters from this third category, for example, could lie about their preferences in order to get a better outcome. We will see some other examples at the end of today's lecture of this. So these are all things that are happening here. So regarding the last point, that voters are better off by lying about their preferences, that's certainly an issue with plurality. But as we are going to see in a couple of lectures, and I'm going to, I think, just at least mention the theorem in today's lecture, this basically happens with every voting rule. So every reasonable voting rule can be strategically manipulated. Unfortunately, so there's not really much that we can do about strategic manipulation there. But these other aspects, like that a candidate is selected, even though a majority thinks he's the worst candidate, that is something that we can do something about. Okay, so let's just summarize these points. Trump is the worst choice according to a majority of the voters. 60% don't like him at all. This is a funny thing is, if you look at this preference profile here and you reverse all the preferences, okay, so like all these voters become completely crazy and what is the last rank alternative becomes the first rank alternative now, then Trump is still the winner, right? And if something like this happens, if a voting rule selects a unique candidate and you reverse all the preferences and then it's still the same unique candidate, this is called a preference inversion paradox. So this is something that it should not happen. If there are ties, of course, things like this could happen, but if there's a unique winner, you reverse all the preferences and it's still the same unique winner, it seems very counterintuitive. And of course, obviously here in this case, it's just because, well, 60% think Trump is the worst candidate. If you reverse all of this, 60% think that Trump is the best candidate. So all of these things that I'm listing here are related to each other. One other thing is that Trump loses all pairwise majority comparisons. And for this, let's try to draw a figure similar to the one that you have seen before to make this a bit more concrete. So here we have 3 different candidates. So let's draw a directed graph where we have like Kasich here, I don't know, Cruz here, and this is Trump. And now draw these directed edges, maybe in a different color, which specify whether one candidate is preferred to another candidate by some majority of voters. Okay, so for instance, if we compare K to C, okay, Kasich to Cruz, where should the edge go? So what is the majority comparison between Kasich and Cruz? So K and C, what do you think? Yes?
K should go to C.
K should go to C, right? Because, okay, let me highlight this. So these voters here prefer K to C, and those prefer K to C as well, and those are 65% of the voters, which is a majority. Therefore, we have an edge here. Absolutely right. How about K and T? Yes, K is preferred to T. And C and T, so Cruz and Trump? C is preferred. Ted Cruz, by the way, is still active in American politics. John Kasich I haven't heard about for a long while, so I don't know whether he's still doing something. Okay, but that completes this directed graph here. Which are graphs that we are going to start quite a bit in this course here. And as is stated here, Trump loses all pairwise majority comparisons. So there are only 2 pairwise majority comparisons that he's involved in, but that is really a strong argument against not choosing somebody, because if you choose T in the end, like there's a majority that prefers K, and there's also another majority that prefers C. So it's really, so this is what is called a Condorcet loser in social choice theory. Yes? Yes, yeah, definitely. So as I said, so all these points are interconnected to each other. So Trump is a Condorcet loser or loses all pairwise majority comparisons because he is the worst choice according to that is even stronger of a statement. So if somebody is the worst choice of a majority of the voters, this person has to lose all pairwise majority comparisons, and that's an even stronger phenomenon. That's right. But this is something, so losing all pairwise majority comparisons that we will also see in other examples, where this stronger thing doesn't happen. Okay. And of course, so in this example, we also have a candidate that wins all pairwise majority comparisons. And this, as we will see later in this course, is called the Condorcet winner. And like many social choice theorists agree that this kind of candidate should be selected. If there's a candidate that has only outgoing edges, it seems like a pretty good candidate, and then this candidate is selected by many voting rules, but not by plurality. Clearly, because plurality doesn't just take into account this information, right? So plurality doesn't really know the information about pairwise comparisons. It only knows top choices. So it cannot really identify whether K has this special property like it does here.
So, can you also say that K is the thing that messes up the independence of the relevant?
Okay, so you are now going ahead of. So the question was whether K messes up independence of relevant alternatives. Yes, in some sense it does, but this is a concept that we are going to define later in this course. It's one of the properties used in errors impossibility. It's called independence of irrelevant alternatives. So yeah, basically, whenever we have more than two alternatives, these irrelevant alternatives come into play. And as we will see with errors impossibility, this is not a particular problem with plurality, but with any voting rule. So the point that I'm going to make, that I want to make at this point, is just that plurality is not a good voting rule. So there are much better voting rules. But later on in the course, we are going to prove some impossibility theory, which would say that like none of these rules satisfies a couple of specific axioms. Okay, so this is something I mentioned already. This last bullet is kind of amusing. So it's in like 2010. There was a meeting of social choice theorists in a castle in France. And there they had a poll where you could, like each of these experts could approve any number of different voting rules. So they first agreed on some number of voting rules that they think are reasonable voting rules. Then everybody of these experts could say which one he likes. So this method is called approval voting. You can say that this is a good method, this is a good method, and that. And then you just, in the end, count which method is approved most often. And this, under this specific rule, would be the best method for voting between alternatives. The funny thing is that in this poll, it turned out that, or maybe not funny, is that plurality didn't receive any support. So none of these experts approved plurality. So the main message is that everybody, at least of the experts and even some non-experts, see this quite quickly, agrees that the status quo that we are using is not good. But then there are many different alternatives that we are going to learn about in this course, and the experts usually don't agree on which method is the best one. Okay, and that may be one of the reasons why plurality hasn't been replaced with something that is better, because it's not that all experts of the world agree with what would be the best method here. So similar, for those of you who have taken algorithmic game theory, I constantly repeated this message that there's no optimal solution concept in game theory. Same thing is true in social choice. So there are many different rules. Some have these advantages and some have other advantages. But like the strange thing with social choices is that the voting method that you're all most familiar with is probably the worst one, at least from the ones that is being used in practice. Of course, you can imagine even worse ones, which just select the worst candidate under some meaningful definition. But among those that are actually used for voting, this is really a pretty bad one.
Can you say that it is good because at least it is easy to understand?
Exactly, yeah, that's a good point that I should make. The biggest advantage of plurality is simplicity. Right? So it's almost all of the other methods that we are going to study are more complicated. In particular, most of these methods do take more preferences into account than only the top choices here. So in most of these methods that we are going to study in this course, you can submit preference relations or rankings about the alternatives. And this by itself is a bit more complicated. In particular, if you have like 1,000 alternatives and you need to rank order all of these, of course, that's a high burden on the voters. There are some things to get around this. For instance, for some methods, you don't need to order all of them. Or maybe there are some interconnections between these alternatives. Some are similar to each other. Or maybe for some applications like here, if there are only 3 or 4, like let's say like 3 candidates, like in the US presidential election, not the primaries, but the actual election. So rank ordering like 3 different presidential candidates should be easy enough. But definitely, so the biggest advantage of plurality is simplicity. You can't beat plurality when it comes to simplicity. In particular, since especially like many years ago, when computers couldn't be used for voting, it had to be also a method that can be implemented in real life very easily. So where you just write something or you raise your hand or something, and you can just quickly count without needing like complicated computations to take place. Because as I said, in computational social choice, people have proved that some methods satisfy nice axioms, but they're actually NP hard to compute. So of course, that's another drawback then. But simplicity, yeah, is the big advantage. But I'm afraid it's basically the only advantage it has. Okay, so let's see how I'm doing on time. So let me go over like 5 different voting rules, and then we are going to have this 15-minute break. And I'm going to have something to drink for my voice. Okay, so here I'm going to define 5 rules, all of which are used in the real world. Okay, and then after the break, I'm going to show you a pretty interesting example using these rules. First rule, plurality. Okay, we have discussed this already, so this is the most ubiquitous in real life. All of you are familiar with it. It's sometimes also called first past the post, or in German it's relative Mehrheit. It's also used for federal elections for the German Bundestag, for the first vote. So in your voting district, it's basically plurality voting that is being used. You can only vote for one candidate from your district. And that's why, for instance, in Bavaria, so in most of these districts, the CSU gets most of the votes. And if you're basically wasting your vote if you're just voting for a candidate which is from a very small party, which also shows a disadvantage of the system because you cannot express your preferences completely because you can only vote for a single alternative but not rank order the alternatives. But as I said, so it's very simple. Next method is called Borders rule. Maybe some of you have heard about that one before. So has anybody heard about Borders rule? Okay, just very few. But once I explain it to you, I'm pretty sure that you have seen it in some variant. So once we take into account the rankings of the alternatives, and all of these rules are doing this except plurality, then we could, one of the first things that come to mind is probably something like Borders rule. So in Borders rule, we assign points to the different alternatives based on the position in our individual ranking. So if, for instance, we have m alternatives, then we could give m minus 1 points to the first alternative, n minus 2 points to the second alternative, m minus 3 points to the third alternative, and so on. Okay, so if there are 3 alternatives, for instance, 2 points for the first choice, 1 point for the second choice, 0 points for the last choice. So I haven't specified that m is the number of alternatives, but it doesn't really matter. So even if m is 0, if m is 1000, the outcome will be exactly the same because in the end we choose the alternative that gets the highest score. Okay? So in some sense the underlying assumption here is that these ranks, so you have the same distance between the alternatives once you have this ranking. So it's almost like a utility function, but of course if you only have these ordinal preferences, if you only know that somebody prefers A to B to C, it's not necessarily the case that the preference intensity, if you want to call it that way, between A and B is exactly the same as the one between B and C. But it's one method of finding a winner. So this is, for instance, used in Slovenia to elect, I think, 2 of the 90 members of the National Assembly. Variants of it are also used for some academic institutions, or the Eurovision Song Contest, something I guess that many of you are familiar with. So there it's not exactly Borders rule, because the point scheme is a bit different. So I'm not a big fan, so I don't know what it's exactly, but maybe like 15 points for the first rank, then 12, then 10 or something, similar to what they have in Formula 1, for instance. Yes?
In this case, can you also give no points to some people, or can you rank every or can you also give
Okay. Okay, so the question was whether you can give no points to somebody. So that depends. So there are different variants that you could define for these rules. So of course, the point system is the same and fixed for every voter. It's not that you can freely assign points, which would be a different rule, where you can just say this candidate should get 15 points and this only 2 or something. It's only first, second, third rank. And during this course, we will always make this assumption, or the simplifying assumption, that the candidates have complete preferences, so they can rank order all the alternatives. But of course, in many cases, there will actually be another rule which is used in the real life, which I'm going to mention, where you don't have to rank order all the alternatives. You can only rank order 3 of them, and then basically the assumption is that you don't like any of the other ones. You could define a variant of border like this, but usually in the literature, it's just assumed that preferences are complete rankings. Because another related question is what happens if you have ties, right? So you could have like 2 alternatives that you think are equally ranked first, and then you can split the border score. There are different ways of extending this to ties. Okay. Anything else that I need to mention about border? Yeah. So there. Whoops. Okay. Oh no, that's fine. Third rule is sequential majority comparisons. So this is also used in the real world, for instance, by the US Congress to pass laws, and that's known as the amendment procedure. So in that example, it doesn't necessarily have to be a majority, but the basic idea is that we are doing pairwise comparisons between alternatives one after another. Okay, so we can just first, because it seems like majority rule is a good idea if you compare 2 alternatives. We will have a formal theorem stating this in 2 weeks. And therefore, since we can compare pairs of alternatives, we could do something that if we have like, I don't know, 3 different alternatives, we first compare A to B. And then the winner of this pairwise comparison is matched with alternative C. And then we do another pairwise comparison. Okay? Okay, so this is what is called sequential majority comparison. So I think the name specifically says what this is about. And as you can imagine, the ordering of the alternatives does matter. Right? So for instance, when this is used in the US Congress to pass laws, the chairman usually has the power to specify the ordering of the alternatives. And this actually gives him quite a lot of power because if you assume that all the preferences are fixed, by changing the ordering in which alternatives are compared, you can actually change the outcome of this voting rule. So for simplicity, in the examples that we are looking at today, we are just assuming, since alternatives are named A, B, C, D, E, we are just taking the alphabetical ordering. So we are first comparing A to B, and then the winner with C, then the winner with D, and so on. Okay, so that's 3 of 5. Next one is plurality with runoff, which is very common in the real world. So I would guess it's probably the second most used voting rules for political elections behind plurality. Is somebody here from France? Okay, so then you are certainly familiar with that rule. So it's famously used for presidential elections in France, like this year, for instance. So there was a presidential election. The idea is that you first do basically a plurality vote, but you don't immediately select the candidate which has the highest score. You pick those candidates with the 2 highest scores, and then you have a runoff voting between those 2. Okay, so you look at which candidates are ranked first most often, and then these 2 candidates face off each other in a runoff election. So in real life, like in France, there are really 2 rounds of this election. So that means your preferences could change, and they sometimes do change between the first and the second round. When we are talking about this rule in this course, and also today, we are simplifying the assumption by saying that we have a fixed preference profile. We take the 2 candidates with the highest score, and then according to the very same preferences, we are comparing these 2 candidates in terms of the majority comparison. Okay, so this is not only used in France, but also in other countries as well. For instance, this year there was a runoff election between Emmanuel Macron and Marine Le Pen, which Macron won. So if you have followed politics in Europe a little bit, you may have been familiar with this. In some cases, this is also something that is being done in practice because there are these 2 rounds in real life. So if somebody has an absolute majority in the first round, then there is no second round anymore because there's really no point in doing this. But since here we are taking a fixed preference profile and just computing everything right to the end, it really doesn't make a difference. Okay, and the 5th rule that I would like to mention is instant runoff, which is a little bit like plurality with runoff in the sense that there are several rounds here. So this is used in Canada and UK to, I think, elect party leaders, so not on a national level. Also, the Academy of Motion Pictures, Arts and Sciences has been using it. I think they switched to Borders rule at some point. So here the idea is as follows. Here really candidates are being completely ranked ordered, like with Borders rule. So every voter submits a complete ranking of all the alternatives. Then you count the plurality score. So you check how many times each of the alternatives is being ranked first. And then you delete the alternative with the lowest score. Okay? And that means those people who have ranked this alternative first, they don't have a first ranked alternative anymore. And then their second ranked alternative moves up. Okay, so if for instance, I like alternative A the best, and A happens to be the candidate with the lowest plurality score, then A is being eliminated in the first round, and then my second ranked alternative is now becomes my first ranked alternative. I'm going to show you an example for this as well. And then we do the same thing all over again. So we compute plurality scores, we delete the alternative with the lowest score, and if a first ranked alternative is being deleted, then the next alternative moves up. Like a clock auction?
Combinatorial clock auction.
I've heard about these, but I'm not sure how. I can't remember exactly how they work.
On the auction here is market design.
Mm-hmm.
Basically, there's like each round when you choose the preferences, and then like the one with the lowest bids, like just is removed. So.
Sounds a bit like it, yeah. Yeah, there might be some connection here. So I think the most famous use of this is for elections in Australia, where, okay, that's why it's not mentioned. So a variant of this is being used in Australia where it's called single transferable vote. And it's a variant because this is actually for parliamentary elections where in the end you don't select a single candidate, but you want to have a seat assignment in the end for the parliament. So this is a different kind of social choice setting. So far we've only talked about rules which select a single candidate. But the single transferable vote thing called STV is very similar to this instant runoff method. And it also became quite popular. It's quite popular now in the US, so there are large lobbying groups which want to implement this in the US, which probably is a good idea. So it's not one of my favorite rules. So as I said earlier, so social choice theorists don't really agree what would be the best rule, but everything is better than plurality. And like more than 10 years ago, there was a similar movement in the UK, and then there was a public referendum where people could decide whether plurality should be replaced with instant runoff, but in the UK they decided against it. Somewhat unfortunately, I guess, so because there were also some famous academics like Timothy Gowers, a famous mathematician and Fields Medal winner, for instance, was in support of instant runoff, but I think there was like a 2/3 majority for retaining the status quo. But this is also, and for political elections, it's really difficult to change something because also there was some campaigning. So first off, parties don't really want to select the best voting rule. They want to select the voting rule which makes them a winner. And then also the arguments that are being used in the discussion when they try to influence the voters when there is a public referendum like this are not really formal arguments. So for instance, an argument that is being used in the US a lot of times is that a loser can actually become a winner because somebody who doesn't win in the first round as a plurality winner can in the end become a winner because, well, you have several rounds because any rule that is not plurality can make a plurality loser into a winner. And therefore, sometimes these arguments are a bit misleading. So, yeah, in the end, the UK is still using plurality. Yes?
Yeah, I was wondering, so in the UK referendum, was there just a decision between plurality and instant runoff?
Yes, it was. Because otherwise, so once you are comparing more than two alternatives, I said it's always tricky. Then it would be the question, which rule do you use for that? Like in this castle in France, for instance, they used approval voting. I think I never mentioned what rule got most support there, because I said that plurality didn't get any support in this experiment in France. The one that got most support was approval voting, which is the very voting method that they used for selecting the best voting method. But I think they later also tried to get the preferences of the different, it was only 22 experts, and they also gave some rank orderings of the alternatives, and for most other methods, approval voting would have also been done, would have also fared fairly well. Okay, but here it was only a decision between two alternatives. Okay, so let me just show you this here before we go to the break, because the next thing that we are going to do after the break is that we are computing the winners according to these 5 rules for this preference profile here. Okay, so we have 14 voters. Maybe let me quickly explain how this thing is being read here. So we have 14 voters because the number on top of each column states how many voters have this preference ranking. 5 voters think A is better than C, then B, then D, then E. 4 voters think E is the best, then B, then C, then D, and so on. Okay, so the numbers on top of each column represent the number of voters that have these preferences. And after the vote, we are going to identify which are the winning candidates according to these different voting methods. And if you don't need a break, you can try to do it by yourself and then check your results with the ones that I'm going to show you after the break. Okay, so since we are a bit later now, so let's reconvene at 5:40, so which is basically 15 minutes, and I hope to see many of you back after the break. Now let's continue with this profile here that I just sketched. So, so in this profile we have 5 alternatives, A, B, C, D, E. As I said, so we have 14 different voters, so let's just write this down somewhere, because this information will be useful, because for some of these methods, for instance, we will look at pairwise majorities, and now we know that if we exceed 7 voters, we have a majority of voters. Okay, so, that's no good idea. First method that we are going to study is plurality. Okay, plurality only looks at the top choices here. So which alternative will win under plurality for this given A? Okay, so simple enough. Exactly, so that's going what's happening here. Now for Borders rule, we need to assign scores to the different ranks. Okay, so since we have 5 different alternatives, so we start with m-1, so that's just a convention, as I said. So we could also start with 5, but usually it's m-1, so that means we have 4 4 for first-rank alternatives, 3 for second-rank alternatives. That didn't sound good. And 1 for the second to last ranked alternative, and 0 for last ranked alternatives. Okay, and just to give you some idea of how this is then computed in the end, just to make sure that everyone understands how Borda's rule is defined. So for instance, for candidate A, each of these 5 voters, so this represents 5 voters, gives 4 points to A. So that means we have 5 times 4, which is 20 for A. And then it turns out A is only last ranked, so it's 20 points for A. Okay, so the Borda score, as is usually said, is 20 for alternative A. Maybe to give another example, let's look at B as well. So the Borda score of B would be 5 times 2 plus 4 times 3 plus 3 times 2 plus 2 times 4. Okay, yes?
In Borda's rule, is the difference in points between ranks always linear or has
Okay.
the same distance? Because
So,
then we would value first place more than
yes, yeah, it's a good question. So the question was whether the distance between these points that we assign here is always the same in Borda's rule. So in Borda's rule, it is always the same. But in general, there's this class of scoring rules, which is just defined, I think, as what you have in mind as well. So you could also have that for first ranks, we give maybe 10, for second ranks, only 5, and then 3, and then 2, and then 1 or something. But the basic idea of scoring rules is always that there's a fixed score vector, which assigns how many points are assigned for first ranks, second ranks, and so on. And we are using the same vector for all of the different voters, because the underlying assumption is always that the preferences of the voters are only ordinal rankings of the alternatives. We don't ask the voters to assign points to the different alternatives. But Borda's rule is an example of a scoring method. Maybe just to give you the basic idea, for instance, another example would be plurality. That's also a scoring method. And then the scoring vector, which we have on the left-hand side here, would be 1, 0, 0, 0, 0. Okay, that's also a scoring method. Okay, so alternative A had Borda score 20, alternative B had something. So I told you how it can be computed. But that's why I prepared an animation, because I'm lazy, and maybe if some of you did it, hopefully your results are the same. And here it turns out that alternative B has a Borda score of 36, which happens to be larger than the Borda score of C, which is 34, so that one is pretty close, and significantly larger than the other ones, in particular A. Okay, so if we applied Borda's method here, alternative B would win. Next is sequential majority comparisons. And for this one, let me draw how this is being done. So I said we have this sequence of pairwise comparisons, and unless otherwise noted, we are doing these comparisons in alphabetical order. So we can draw this as a tree, a binary tree, which looks a bit like a caterpillar. So first we compare alternative A with alternative B. Okay, and then the winner of this is compared with alternative C. And then the winner of this is compared with alternative D. And finally, the winner of this is compared with alternative E, all pairwise majority comparisons. Okay, so if we do this for this preference profile, so again, we still have 14 voters. So for a majority, we need more than 7. So if we majority compare A and B, which alternative would win? B, okay. Let's just quickly check why this is the case. So for instance, these 4 here prefer B to A, and those 3 here, that's 7, and those as well. A is last ranked by a majority of the voters, therefore it's pretty simple. Okay, so B would win. Now the next pairwise comparison is between B and C. C would win, okay, so since nobody disagrees, I guess I don't have to show you the voters. C and D. C again wins. And C and E. Again C. Okay.
Can we have a tie?
Yes. So in principle, in particular, since we have an even number of voters in this example, there could be a tie. But for the introductory lecture, we are trying to keep things simple, so we try to avoid ties. But in general, there can be ties, and then there are, especially for sequential majority comparisons, there are different ways of how to deal with ties. Yeah. But it's not ruled out in general, of course. Okay, so alternative C wins according to sequential majority comparisons. Yes?
I think before you said that if you would change the order, you can manipulate that.
Yeah.
So in this case, would it be possible to change the order that C does not win?
Great question. So the question was whether we can change the ordering of the pairwise comparisons from A, B, C, D, E to another ordering such that C doesn't win. In principle, that's possible. And sometimes in the first lecture when I had more time, I was showing examples where this is the case. For this particular example, it's not possible. So the nice thing about this example is that no matter which ordering of alternatives you take, the winner will always be alternative C. And I'm going to show you why this is the case by just looking at all the pairwise majority comparisons between all pairs of alternatives. Okay, so we have a total of 5 alternatives. So now let's do a bit of combinatorics. So how many pairwise comparisons are there if we have 5 alternatives? So like A versus B, A versus C, and so on. So if 11, no? Yeah, 10. Yeah. How did you compute it?
It's 5 times 5 minus 1 over 2.
Yeah, right. Yeah. So there are many different ways of. So you could also take 5 times 4 and then divide it by 2. So like all of these 5 alternatives are paired with like 4 of the other alternatives, but then you are counting every pairwise comparison twice, right? And therefore we have to divide it by 2. So, but what you said is right as well. So it's for me, I usually think about it like 5 times 4 divided by 2. Like every alternative has 4 opponents, and then we are counting every comparison twice. So that means we have like 10 different pairwise comparisons. And therefore we can draw like a majority graph like the one that I've shown you before. And let's see. Right. And if we do this, it looks like this. And once we have a look at this graph, it becomes fairly obvious why for any ordering of the alternatives A, B, C, D, E, which was your question, the alternative C has to be the winner. Because in this example, C is majority preferred to all 4 of the other alternatives. So it is what we earlier informally called a Condorcet winner. So it wins all pairwise comparisons. So therefore the ordering doesn't matter, because at one point C will always be the winner in this in any sequence of comparisons, and then it will never lose again. Right? So just as was the case for the ordering A, B, C, D, E. So we compared A with B, then we compared B with C. Well, then clearly C won against B, and once we are at C, it will win all pairwise comparisons. We will never go back. Okay, and at some point we will always end up at alternative C. That means for all the orderings, so it's actually much stronger than what is stated here. So for any ordering, the winner will be C. Okay. And interestingly, so as you can already see, so these are different. So there are different arguments and different winners here. And maybe this seemed like a pretty weird argument, taking the sequential majority comparisons in one particular order. But since in this example the ordering doesn't matter, and we have a so-called Condorcet winner, which is majority preferred to all the other alternatives, this becomes a very strong argument. Like most rules that we are studying in this course will have this property that if there is something like candidate C here, it needs to be selected, because it wins all pairwise majority comparisons. Okay, so now we have 3 rules, 3 winners. You can probably already see where this might be going. Next one is instant runoff. So with instant runoff, we look at, okay, so we again look at the plurality scores. So we only need to look at first ranks. And then we delete the alternative, or we eliminate the alternative which has the lowest score. So which alternative here would have the lowest score if we only look C? Great. Because sometimes people are being misled and think that it would be B, but C is never first rank, so the plurality score would be 0. So that means we can delete C. Okay, let's just delete it here. Okay, now C is not there anymore. Now which alternative now has the lowest plurality score if C isn't available anymore? B, right? Okay, so we delete B. And now something interesting happens, so which is important for instant runoff. So now these last 2 voters don't have a first-ranked alternative anymore. That's why the second-ranked alternative is just moving up. Okay, so that means D now becomes the first ranked alternative for those two voters. So that means the score of alternative D would be 5 now. And then, okay, it becomes easy. So A has 5 as well, and E only has 4, so E is being deleted next. And which alternative now needs to be deleted? A, right? Because like even those, oops, well, that's not what I had in mind. Even those 4 people here think D is better than A, so therefore A needs to be deleted, and then the winner becomes D. Maybe not completely surprisingly at this point of the example here. So with instant runoff, I think there's also an animation where this is being done, which hopefully does exactly what I just did. And then, yes, alternative D wins. Okay. Last rule in the example is plurality with runoff, which is the rule that is used for presidential elections in France. Let's delete or remove all of these notations here. So here we take the 2 alternatives with the highest score. Again, we are talking about plurality score. And then these 2 alternatives face off in the majority comparison. So which 2 alternatives would that be? So A, of course, and E. Right, so A and E are facing off. Now, if we recall, we actually looked at all the pairwise comparisons. So we had this large tournament graph. So it's a directed graph, which is a complete directed graph. There was also the comparison between A and E. If you don't recall it, we can just do it manually again. Well, again, we know A here is the least preferred alternative of a majority of the voters. So a majority prefers E to A, which completes the example, like to a maximum, hopefully, shock effect. Because in this preference profile, alternative E will win if we are using plurality with runoff. And the puzzling thing is that all 5 of these rules are being used in the real world, right? So that means depending on where those 14 voters are going to make a collective decision, the outcome will be completely different. So therefore, the first point that I wanted to make in this introductory lecture is that plurality is not the best voting method. And then there are many other methods, each of which sounds quite reasonable. Like maybe sequential majority comparisons, if you hear it for the first time, you think, okay, the ordering is really important, but in the example, the ordering doesn't matter at all. So it becomes quite convincing. If some alternative wins for any ordering of majority comparisons, this thing should be selected. But there are 5 different winners. And I think that really shows the essence of why social choice theory is so interesting. Because I think you can convince a layperson of the reasonableness or usefulness of any of these rules. If I had just shown you the definition of one of these rules, you probably could be convinced, because I could also show you some properties that are satisfied by these rules, some examples where they give some intuitive outcomes. It's easy to convince laypersons that a rule is a good rule. And for all of these rules, the definition seems quite straightforward and intuitive. So there are some shortcomings for plurality because so much of the information is ignored, but Borda's rule seems reasonable. Instant runoff also seems like a good idea. That's why these rules are actually used, but they lead to completely different outcomes. And in order to shed some more light on which rule should be selected under certain circumstances and what are the pros and cons of these different rules, the axiomatic method is used. I think this example also shows why the axiomatic method is so important. So the definition of all of these rules is reasonable. So as I said, you can convince somebody that instant runoff or Borda's rule is a good idea. But this is true for many other rules as well. But once you define axioms, like certain properties that a voting rule should satisfy, maybe just to give you an example of what kinds of axioms I have in mind. So these are not really necessarily like complicated technical mathematical axioms, but they should be intuitive properties that voting rules should satisfy. So for instance, one of these properties says that if we have 2 different electorates, so 2 disjoint sets of voters, and we apply a voting rule for the first electorate, and then alternative A wins, and then we apply the voting rule to the other electorate according to their preferences, and alternative A wins as well. If we merge these 2 electorates into a larger group of voters, then alternative A should still be the winner. Right? So that seems like a reasonable axiom. But this axiom is only satisfied by 2 of these rules. 3 of these rules violate this axiom. So just to give you an example of what kinds of properties we have in mind when we talk about axioms. And interestingly, the axiomatic method in social choice has not only produced results of the kind, so this rule satisfies this property, so these are usually quite straightforward. There are some exceptions where just proving that a property is satisfied or disproving is extremely difficult. And during this course, we will encounter some rules for which I cannot even tell you whether a certain property is satisfied. But in most cases, this is known. And there are also these like far-reaching impossibility results where you just, as I mentioned earlier, take a bunch of axioms and then you can prove that no rule satisfies all of them. Okay, so I think that is a nice motivation for looking at axioms. Oh, yeah, one thing I forgot. If you look at this example, of course, the example was designed to have this particular effect. This one was even designed by a computer to do this. So I think the first time when I got interested in social choice theory, I saw an example similar to this one, which used slightly more voters, by Michel Berlinski, which was published in a science magazine. So that really got me started in social choice theory, more than 20 years ago. And at one point, I think last year or 2 years ago, we kept coming back to this example, and then we tried to find the smallest example of this kind for these particular 5 rules using integer programming. So this is also an example where you can see that computer science can contribute something useful. So many of these voting paradoxes and examples were constructed manually by political scientists and economists. So in some papers, they are just referring to a previous example which was constructed by a famous researcher 30 years ago and so on. And it turned out that many of these things can be constructed very efficiently using computers. Like this example, for instance, I think the integer programming just took 1 or 2 seconds to solve. And the constraints that we had is we wanted to have the smallest number of voter types, and of course 5 different winners. So it's even possible to find this. So this example has 14 voters. So there's an example that only uses 12 voters. So it's even smaller, but it uses more different voter types. So the other example uses 7 different types of voters. So that means we would have 7 columns rather than only 4 columns here. That's why I picked this one here. But I think just for, even if it's only for like educational purposes, like constructing examples like this is quite nice. All right. Now let's look at some axioms. So in today's lecture, I will only talk about 2 axioms, which I'm not even defining formally. So again, if you're a mathematician, you might be a bit disappointed that I'm just like bubbling about the axioms, but not really specifying formally what I mean. But we don't have a formal model yet, and in the interest of time, I think for these 2 axioms, they can be specified quite quickly without using formal mathematics. And of course, we are going to define them later on in the course. The first axiom is called monotonicity. And so even non-mathematicians have seen monotonicity in many different forms. So there are many different properties called monotonicity in many different areas. In social choice, it means the following. If we have an alternative that is chosen, so that means it is among the winners selected by a social choice function, and then we reinforce this alternative, which means we are moving it up in the preference ranking of one voter and not change anything else. Okay, so we don't necessarily need to move it on top of the preference ranking of one voter, but we only make it stronger in the sense that it is now better than more alternatives than in the original preference profile. And then the consequence of this axiom is that this alternative should still be chosen. Okay, so this seems like a very mild and intuitive axiom. So some candidate is a winner. We only make it stronger in the sense that we are moving it upwards, then it should still be a winner. So maybe one intuition. So even if you, first of all, like mathematically and intuitively, it seems very clear that a property like this should be satisfied. But even if you don't agree with that, you can think, for instance, of an application where the different candidates are campaigning. So the preferences are not fixed. So in this course, we are assuming the preferences are fixed. But you can have a model where preferences are not fixed, and then candidates can convince the voters which properties they have and try to convince them to vote for them. And if monotonicity is violated, then you can have a case where somebody convinces more voters to vote for this person, and this actually makes the winner into a loser, right? If monotonicity is violated. And this is something that should not happen. So if the more voters you convince of voting for you, also a candidate that wins an election should still be a winner of the election. So I'm specifically talking about a chosen alternative here. because as was mentioned earlier, so there can be ties in general. So all of these social choice functions that we are studying can have ties under certain circumstances. So for simplicity in today's lecture, we always talk about single winners, but you can easily imagine that there are many clear-cut cases where you cannot select a single alternative if you want to satisfy basic fairness conditions. So for instance, if you have two voters, two alternatives, one of them prefers A to B, the other one prefers B to A. So we cannot select a single alternative without breaking basic fairness or symmetry conditions, which we are also going to define later in this course. So these are called anonymity and neutrality, which basically say that alternatives and voters should be treated equally. And in these cases, for instance, there will be several winners. And therefore, monotonicity is also defined for sets of winners. And it just says if A is among the winners and is being reinforced, it should still be among the winners. So it doesn't say anything about other potential winners to make it as weak as possible. There are other axioms that do, but this axiom just says if A is among the winners, it should still be among the winners if it's being reinforced. Interestingly, so this kind of axiom was violated for German Bundestag elections. But I have to make sure here that you understand that this is a different model here. So because for the Bundestagswahl, we are talking about parliamentary elections where we are not voting for a single candidate. It's not like a US presidential election where there is just a single winner. But here the outcome for a Bundestag election, the outcome is just a seat assignment. So we assign seats to different parties. And there's an equivalent of this monotonicity notion which says that if more voters vote for a certain party, so then the number of seats that this party gets in the parliament can only increase, but not decrease. Okay, so that seems like a natural property, but it's for like a different type of election where the outcome is a seat assignment. And this was violated, interestingly, and then the government actually changed this. So there was a committee which recommended to the government how to change it. And in this committee, there was a mathematics professor from Augsburg, Professor Pukelsheim, who gave a guest lecture about this many years ago in this course in computational social choice. And this change, by the way, is also the main reason why we now have such a bloated parliament. So for those of you interested in politics, you may know that the number of politicians in the parliament is growing and growing. And this is because this monotonicity failure has been rectified. So there are some drawbacks going on with this. But this is just, all of this is just a side comment because this is about seat assignment, which is a different type of elections that we are usually talking about in this course. So in this course, we are talking about the simpler case where we are just voting for one single alternative, where the outcome is just a single alternative or a set of alternatives, but not an assignment of parties to seats. All right, that's monotonicity. The other property that I'm going to define, or informally define today, is Pareto optimality. So who has heard about this term before? Okay, some. So at least those who took algorithmic game theory should be familiar with this. So this is probably the single most important property in microeconomic theory. So it's a very basic property of optimality. It's a very weak notion, and that's why it's so influential. In the context of social choice, it means the following. An alternative A should not be chosen if there's another alternative that everybody prefers to A. Okay? If there's another alternative B that everybody prefers to A, then A should not be chosen. That seems very straightforward, right? So, because usually social choice is about compromise. So we have these possibly conflicting preferences, like two people, one likes A, the other one likes B. But if everybody agrees that A is better than B, or in the example I said, it was if everybody agrees that B is better than A, then A should not be selected. So this property doesn't say which alternative should be selected, but A should definitely not be selected because we can find something else such that everybody is better off. And this is also the basic idea of Pareto optimality in many other areas like game theory and economics in general. So if you can find a social outcome that makes everybody at least weakly better off and maybe somebody strictly better off, then we should pick this other social outcome. So there's no compromise, no drawback, everybody is happier. Maybe some are equally happy off. But the way I defined it here, because in most of this course we are going to have strict preferences, we can just say only if something is, if everybody prefers one alternative to the other, then the dominated one should not be selected. Okay, so these two properties seem like very mild conditions, right? I hope you would agree that any social choice function should satisfy. I'm not going to show you an impossibility, by the way. So, but this some impossibilities are like this. So I'm going to show you some properties, trick you into try to convince you that these properties should be satisfied by any function, and then one slide later I'm showing you that no function satisfies both of these properties. But that's not the case here. Because for today, okay, so Pareto optimality, in case you were wondering why it's called like this, is named after Vilfredo Pareto, an Italian economist. But what we are doing now is not prove any theorem, but we will only check for these 5 rules that I have introduced which property is satisfied by which rule. Okay. First, plurality. Okay. And we only want to know whether it satisfies monotonicity and Pareto optimality, just to have some comparison, because I said all of these rules are used in the real world. So if maybe some property is violated by some of these rules, we already have an argument against at least one of these rules. Monotonicity. Okay, monotonicity means if an alternative wins, it should still be the winner if it is moved up in the preference ranking of one of the voters. So who thinks that monotonicity is satisfied by plurality? Okay, so who thinks it's not satisfied? And everybody else has no clue or didn't listen. But yes, so let's try to have a semi-formal proof of why monotonicity is satisfied. So basically everybody here thinks that it is satisfied by plurality. So what changes if we move something up? So first of all, things can only change if we replace a first-ranked alternative of one of the voters. Okay, and if we do this, then the alternative that we are moving up gets a strictly higher plurality score, and the alternative that it is replaced with gets a strictly lower plurality score. And that already proves that the score of the alternative that we are moving up can only increase. The other ones remain fixed or maybe decrease, and therefore the winner has to be the same. Okay, so monotonicity is satisfied, fair enough. Pareto optimality. So here we need to look at the case where now let's say we have 2 alternatives, A and B, and everybody prefers A to B. So is it possible that plurality, maybe under some strange preference profile, picks alternative B, even though everybody likes A better? No, it's not. This is almost like a trick question, right? So because if everybody prefers A to B, what can we say about the score of alternative B?
0.
Yeah, it's 0, right? So it can never be ranked first. So we assume strict preferences still. Therefore, clearly, Pareto-dominated alternative cannot be selected. Okay, good enough. So after all the bashing of plurality, at least it gets 2 check marks here. Borders rule. Monotonicity. So I give you some seconds to think about this. So we are reinforcing a winner. Mm-hmm. No, any number of alternatives, not only 2 alternatives.
Wasn't the example you showed in the very beginning with Trump that proves that against Pareto optimality, that everybody thinks that Cruz is better than Trump, but Trump's still won the election?
Okay. So again, I repeat it for the recording. So the question was whether in the Cruz, Trump, and Kasich example, Trump was Pareto dominated because everybody thinks that Kasich is a better alternative, but that was only a majority. So it wasn't the case that everybody thinks that some alternative is better than Donald Trump. So there was a majority, I think it was 60%, who think that any of the 2 other candidates is better than Trump. But for each of these single pairwise comparisons, it was only a majority, but not unanimity. Yeah. Okay, borders rule and monotonicity. Yes? Okay, so it's obvious that it satisfies monotonicity. Okay, yeah. So it's it's very similar to the argument for plurality. So only that if we now put A on top of B, well, then the border score of A strictly increases, the one of B strictly decreases, and then, well, if A was the border winner before, it still has to be a border winner afterwards. So monotonicity for all scoring rules is obvious, right? So these are only 2 examples of scoring rules, but for all scoring rules it works. Okay, well. Who thinks that borders rule Okay, Pareto optimality for borders rule. It's not as clear as for plurality, because for plurality I said that the score will actually be 0. Now with border scores, a Pareto dominated alternative doesn't have to have a score of 0, because in Border's rule, some candidate only has a score of 0 if it's the last rank candidate for all of the voters. That doesn't have to be the case here. But if everybody prefers A to B, well, then the border score of A is definitely larger than the one of B, so therefore B cannot be selected. Okay, so that's again, it's like a proof, so you can write it down formally and then it's a proof. Sequential majority comparisons. First, monotonicity. What do you think? Yes?
Yeah, if the order of the checks doesn't change, then
It's, yeah.
it should fulfill the monotonicity, because as soon as the first check happens, and for example, alternative A is larger than this check and then continues to be larger than everything else, if you just add, if you just have one voter who votes more for it, then it also wins this particular comparison and or succeed votes.
Okay, yeah. So I'm not completely repeating this argument, but it's so if the ordering remains fixed, so in our examples it was always the alphabetical ordering, so then you can only make majorities stronger by reinforcing an alternative, and then if an alternative was the winner under some fixed ordering, and then after reinforcing this alternative, it would still be the winner. How about Pareto optimality? So is it possible that under sequential majority comparisons an alternative B can win even though there's another alternative that everybody prefers to B? Yes? So I didn't tell which one. I don't know. You. Oh.
So in the competition of both, if there is a B that is higher in all, in the competition of both, B will pop up and then B will disappear.
Okay, so so say we have this Pareto dominance between A and B, so everybody prefers A to B, so it's just a super large majority. It's an example of a majority. A will definitely win against B, so that's right. Do you have the same argument? So your claim would be that it satisfies Pareto optimality.
No, my claim is like there can be like other possible computation trees so to speak that everyone can be better off. I think that if we change the order of computation, then we may find.
Okay, but so the comment was that if we change the ordering of the alternatives, but the ordering remains fixed, but of course we can change the preference profile. So if you want to prove that it doesn't satisfy Pareto optimality, we can try to construct a preference profile where Pareto optimality is violated for the ordering A, B, C, D, and so on. So who thinks Pareto optimality is satisfied by SMC? Okay. Who thinks it's violated? Okay, and the other ones are unsure. So there was almost like a tie, it seems. I think I raised some doubt by the way I was discussing with you. And indeed, it violates Pareto optimality, which perhaps is like the first really surprising axiomatic example that you are seeing here. So this example that you are seeing here does exactly the job of that. Just to give you, before we go over the example, just the idea of why this is working is because, or maybe let's look at the example in particular already. So we have these 3 voters and 4 alternatives here. So first, I claim that there's some Pareto dominance here. So some alternative is preferred to another alternative by all of the voters, which would be this pair of alternatives. I have to check myself. Okay, now I see it. So yes?
A dominates D.
Right, so everybody prefers A to D. Okay, so D should definitely not be selected. Okay, and we can now compute the voting tree here, and it will turn out that D will be selected, even though it's Pareto dominated. But the ordering will be A, B, C, D, so it's related to what you were saying. So we are never doing the pairwise comparison between A and D, right? So, we are doing the comparison from first A versus B. Okay, which is, since it's only 3 voters, this is pretty straightforward. So alternative B wins, right? Now the comparison with alternative C. B versus C is C. Okay, and finally alternative D versus alternative C. C. No. D. Yes, D does win because this voter prefers D to C and this one prefers D to C. Otherwise, the example wouldn't work. That would be bad. Okay, maybe let's use a different color here. So alternative D wins, even though, maybe let's use blue for this, we have that all of these voters think that A is better than D. Okay, and this example requires 4 alternatives. It doesn't work with 3. So I think that, as I said, is already a kind of surprising result because we did the vote here, so like almost half of you would have believed that sequential majority comparisons does satisfy Pareto optimality, but it's possible to select an alternative which is Pareto dominated, and that means there's another alternative that everybody thinks is better, okay, which I think is pretty problematic. Also, if you think about the fact that this is being used to pass laws in the US Congress, for instance, it's a bit concerning.
The example when you compared all the voting groups was the C was the winner.
Yeah.
Was it Pareto dominating all other options?
As far as I know, I think in the example there were no Pareto dominances.
Because we see like the C was preferred, like it has the most arrows.
Yes, it was a Condorcet winner, that's right. But I think there was no Pareto dominance, which means, so it wasn't the case that all, I think 14 of these voters preferred one alternative to the other. That's actually rarely the case, as you could imagine. If you look at large random preference profiles, it's rarely the case that one alternative is better than another alternative according to the preferences of all of the voters. Okay, so Pareto dominance is, Pareto optimality is violated. Plurality with runoff. Okay, so maybe for some of these rules you need to like think again how they are defined. So that was the French election system, where you have a runoff between the 2 best candidates according to plurality. Does this satisfy monotonicity? I guess now you're becoming more skeptical in general, but so who thinks it satisfies monotonicity? Who thinks it doesn't? Wow, okay, fooled you again, it violates monotonicity. And the reason for this is, so again, monotonicity means a candidate is a winner, and then we only make it stronger, and then it becomes a loser. Okay, and the reason is that we can make, so we have to reinforce this alternative against some other alternative, and we are not reinforcing it against the alternative that it wins again in the runoff election. So we reinforce it against another alternative, and that changes which candidate goes into the runoff election. So that's how we can actually trick this thing. So let's look at the example why this works here. So this is a more general example. It works for a couple of voting rules, not only plurality with runoff. That's why it uses a bit more voters here. So here we have 17 voters. 17 voters. And now we take the ones with the 2 with the highest plurality score, which would be alternatives A and C? A and B, right? So because those here, so these 6 voters here prefer B the most, okay. This representation may be a bit confusing, but you will get used to it. So 6 voters prefer B the most. That's why there's a runoff between A and B. And then between A and B, we are doing a majority comparison. And which alternative wins in the majority comparison between alternative A, right? Because 11 voters prefer A to B, so alternative A wins. Okay, and now if monotonicity is violated, it is possible that some of these voters move A upwards in their preference ranking, and A then becomes a loser. And this is exactly what's happening here, so I've marked which ones are changing. So these 2 voters here move A above B here. Okay, and then we get the following preference profile. So as I said, so they are reinforcing alternative A against the 3rd alternative, not the one with which A had the runoff election. And then if you look at this new preference profile here, the score of A is now 8, but now A is not being compared to, before it was B. Okay, okay. So here there was the comparison between A and B. And now in the second profile here, when A is being reinforced, now the comparison is between A and C. Okay, so we have actually reinforced A against the other alternative in the runoff, but by doing this, we have made sure that A is now being compared to a different alternative, C, And if we now do the majority comparison between A and C, it turns out that C wins. Right? Because like 9 of these voters here prefer C to A, and therefore C wins the majority election. So A becomes a loser, even though the only thing that changed is that these 2 voters moved A on top. And there are actually papers which are studying how many times this probably happened in French presidential elections. Because we cannot really know for sure, because we don't know the exact preferences. We only know what the top choices that the voters submit. But of course, there are polls and everything, and we can make some assumptions of what the preferences probably looked like. And this is really curious because it's, as I meant earlier, if monotonicity is violated, it means that, for instance, in the French presidential election, it's possible that a candidate tries to convince more voters of his policy or her policy, then more voters think highly of this candidate and move him upwards, just like in the example here, and this makes the candidate lose rather than make him remain a winner. So that shows that plurality with runoff violates monotonicity. Okay, how about Pareto optimality and the same rule? I know it's getting late now, but so yes.
I don't think that this is violated, because if you have like alternative A, which is always above alternative B, so to speak.
Yeah.
Then if we do the plurality and the runoff, so basically like you would always get alternative A to the top row first before you get alternative B to the top row. So alternative B couldn't win the runoff.
Right, so I think it's even simpler than that, right? Because once we talked about plurality, we said that if A Pareto dominates B, then the score of B is 0, right? So it's never first ranked. So Pareto dominated alternative can never get to the runoff. And therefore, and also on the so if we have except no, it can never get to the runoff. So it depends on how we define it. If you have only 2 alternatives and everybody prefers A to B, you can say there's a runoff between A and B, but then of course that would be in favor of A then. But as I said, so usually in real life, if there's an absolute majority, we just pick this alternative and there's not even a runoff. So the plurality score of a Pareto dominated alternative will be 0, so it won't get to the runoff. But it's interesting how you become more and more skeptical, because that's really what social choice is about. So some properties seem so like mild and uninteresting that you think like every rule needs to satisfy it. But in this case, Pareto optimality is satisfied. Now, instant runoff. Okay, so instant runoff is perhaps out of the ones that I showed you the most complicated one. So it was the one where you delete the alternative with the lowest score, and then alternatives can move up and so on, and you have many rounds until then finally you have a winner. So I think for this one it's pretty hard to see whether it satisfies monotonicity or not. But still, maybe you have an intuition. So who thinks monotonicity is satisfied? Okay. Who thinks it's not? Okay. A few do. Okay, but most think it is satisfied, but it's not. And here I can actually save some space and time, because this example here is universal, so it works for basically any runoff method. So for 3 alternatives here, instant runoff does exactly the same thing as plurality with runoff. So it deletes the alternative with the lowest score, which basically is the same thing as saying that we take the 2 with the highest score into a runoff election. Unless there are ties, it's the same thing, right? So we delete the one with the lowest score, we take the ones with the 2 ones with the 2 with the highest score. And therefore, in the example, instant runoff will do exactly the same as plurality with runoff, and therefore monotonicity is also violated. And you can also define other runoff methods. So for instance, in general, you can have a runoff method where you do everything with border scores. So you take the 2 alternatives with the highest border score, and then they have a runoff election, for instance. But in this simple example, because there are only 3 alternatives, this rule would also do the same thing. So this example is pretty universal. It was constructed by Peter Fishburne, I think, and shows that runoff rules all violate monotonicity. And the basic idea, again, is that once you have these several rounds, so whenever you define something in different steps, also in other areas, not only social choice, then there's always the risk of losing monotonicity, because in one round you do one thing, in another round you do another thing, and this, like on a high level, is the reason why these runoff methods violate monotonicity. Pareto dominance. guess that one we can again do quickly, right? So if everybody prefers A to B, then the probability score of B will be 0, and then it will usually be, unless there are ties, it will be the alternative that is deleted first, and therefore it will not win under instant runoff. And therefore this property is satisfied. So this completes this simple axiomatic analysis of 5 rules and only 2 properties, and 2 particularly simple properties, but it already shows that some of the rules that seemed very innocent and like they would probably satisfy all reasonable properties, surprisingly violate things like monotonicity or even Pareto optimality. So monotonicity, so of course you cannot compare those things directly, so they're logically independent from each other, but the failure of Pareto optimality seems really severe, at least to me, right? Because it means you select something even though everybody agrees something else is better. Okay, so for the remaining time, I would like to show you, because as I said, just a second, for today's lecture, I want to give you a very broad overview. So for the remaining time, I will show you similar examples where we talk about strategic manipulation and also strategic abstention, because that's something that we are going to cover later on in this course, so probably only next year. Yes, but you had a question.
My question is, I wonder if there are any actually kind of relevant algorithms that fail Pareto optimality, but not in a somehow corner case, impossible scenario. Like in the case that.
So by algorithms, you mean voting rules, right?
Voting
rules,
yes.
Okay. Yeah, just.
So for the, I forgot, SMC failed Pareto optimality, but there it only fails if. So I think if no one. Kind of, you would not choose an order in which it would win if no one wants it, but no one wants it.
Okay, but it's like the ordering is assigned beforehand. So you first fix the ordering usually, so it depends on what kind of application you have, and then you get the preferences. So just to summarize, so what you are concerned about is that these are corner cases. So also for other counterexamples that we are going to see, you can have the impression that maybe this is like a weird counterexample that is contrived and unrealistic, and in 99% of the cases that's not a big deal, right? So does that summarize to some extent of what you are concerned about? This is true for some failures of axioms, and that is something in general that you can always ask yourself once you have like an axiomatic failure. So if a property is violated, is it usually violated, or almost always, or almost never? So we will rarely, so for some cases we will discuss this question. So there's one particular example where the answer is actually quite exciting. But I think for this particular example, of course, so I wanted to say that Pareto optimality failures of SMC are quite often, but of course it depends on what your distribution of preference profiles is. Because as I said earlier, so when you have large electorates and like randomly draw preferences, it's quite unlikely that the alternative is Pareto dominated at all. Right? If you have like 1,000 voters and you randomly draw preferences, it's quite unlikely that everybody prefers A to B. But nevertheless, like especially if you have like preference profiles with small numbers of voters, I think it would be quite common, like in the example here, that Pareto dominance is violated by sequential majority comparisons. And then, of course, you can also take the point of view and say that even if it only rarely fails, I wouldn't want to use a rule which in some few corner cases really screws up badly. Like, say, if it's a very important collective decision that you're making, you don't want to have the possibility that something may go wrong. But it's a bit like, so this axiomatic study in social choices is a bit similar to what people usually do in computer science, because in computer science, the analysis of algorithms is sometimes also criticized for being almost completely, or like to a large part, focusing on the worst case. So what's the worst case that can happen? So the worst case running time, for instance, for an algorithm. Whereas here, usually we are also concerned with worst cases. So if something can happen, it's bad. And we want to rule out completely that an axiom can be violated. Okay, but now for the remainder, just some examples for strategic manipulation. So as I said earlier, manipulation means just, so I think the term is a bit misleading, because manipulation sounds like it's something illegal. So it's like you're doing something that is not allowed by law. But in the context of social choice, it just means that you're not being truthful about your preferences. And like many of us have done this in elections. So if you know, so for instance, also in US presidential elections, so there's usually these two big candidates, and then sometimes there's a third candidate like Ralph Nader many years ago from the Green Party. So they usually don't have a chance of being elected. And if you vote for this candidate, you can make a statement, but of course, so this candidate in most cases have no chance of being elected. So therefore, if you have preferences, if you, for instance, think that this Green candidate is your most preferred candidate, but you also have preferences over the Democratic and Republican candidate in the US, then you can vote strategically by giving up your most preferred candidate, and then, for instance, like many people who prefer the Green candidate the most probably also prefer the Democratic candidate or the Republican candidate in the US, and then misrepresent your preferences accordingly. So that's why I'm saying, so it's not really a manipulation in the sense that it's illegal, it's just that you are misrepresenting your preferences.
More like hacking.
Yes?
Going back to the presidential election in the US,
Yeah.
to really strategically manipulate, you always need like some notion of what is possibly going to happen.
Yeah. Yeah, okay, so that's certainly true, and once we are talking about this in more detail, at like probably next year, so this will be an important factor. So the comment was you need to have some information about the preferences of the other voters in order to be able to manipulate. So for instance, if it's like, I think that was many years ago, so you were probably too young there, but for US presidential elections, it was at one point it was Bush versus Nader, and Bush, Gore, and Nader. So Gore was the Democratic candidate, Bush was the Republican candidate, and then there was Ralph Nader, the Green candidate. And only if you know that the preferences of the other voters are such that Nader has no chance of being elected, then you can manipulate. So if you don't have this information, of course, then it's difficult. But in many cases, you do have this kind of information. For instance, in US presidential elections. So it was no secret that the Green candidate gets, I don't know, less than 2% or something. Okay, but in the interest of time, let me show you perhaps a bit more concretely what we mean here. So voters are better or can be better off by lying about their preferences. So this example here is Borders voting rule. So here we have 7 voters. Again, we could now compute the border score. We have done this in other examples before, so I hope you trust me that alternative B gets a border score of 14 and wins the election. And now there are several possibilities of how voters can manipulate here. I think the one that I'm going to show you is, for instance, take the voters in the second column. So those here. So they are not particularly happy with the outcome. Okay, so B is like their third ranked alternative. And here you can see that alternative C has already a pretty high border score. Okay, so what these people, for instance, need to do is, well, they can just, both of these can do it together, for instance. They can move C upwards, and at the same time, they can also move B downwards, or maybe one of them suffices then. So you move C upwards, which increases the score of C, and you move B downwards, which decreases the score of B. Okay? And then the outcome will be alternative C, and these people who change their preferences are better off. So that's an example of a manipulation. So there are some voters who are, but of course, as you said, this is under the assumption that the voters know the preferences of everybody else. So in this case, it seems maybe a bit unlikely that you know exactly those preferences, but in some examples, like in the US presidential election, there's only 3 candidates, and it's almost common knowledge like what the preferences of the voters look like. Also, in some cases, there are committee elections, like if you have a faculty meeting, for instance, at TUM, for instance, in some cases, all the different options are being discussed among the professors, and it's already pretty obvious which professor prefers which alternative, and after the discussion, there's being a vote, and then you already have gathered a lot of information about what the preferences of the others are, and then in some examples, you can do something like this, because then you know, with Borders rule, it's particularly simple. If you know let's say you prefer candidate A very much, and the prime competitor of alternative A is candidate B. You have learned this from the discussion. Then it's of course pretty straightforward to, no matter what you think about B, to put B at the bottom and A at the top. Because if it's likely that B is the main competitor, then you can maybe, in some cases like this one here, make the difference between the selection of A and B. Okay, so yes, so any voter from the second column suffices, so it doesn't have to be 2. The same example also works for plurality. There's only the annoying thing there that if we only change the preferences of a single voter, we cannot make it a clear-cut example where there are no ties. So if we only change the preferences, the preference ranking of one single voter, we can then maybe in one case we have 2 plurality winners and in the other one we have only 1. So therefore, if we want to make this example more convincing, we can have 2 voters change their preferences at the same time for plurality. So that means that, like, the first 2 rules that we had in our list of rules already can be strategically manipulated. So there are examples here which do exactly this job. Come on. Okay, so that is just like the semi-formal definition of what strategic manipulation is. So there's a preference profile which yields a single winner. So at this point, we only define single winners to each other. So because once we allow for ties, then it's not exactly clear how you can compare sets to each other. Maybe in one preference profile, candidate A, B, and C win. Maybe in another preference profile, A and B win. And then it's not clear whether you really prefer this set to the other set. We are going to study this in particular, how to compare sets. But for the beginning, in this course, when we talk about manipulation, we only compare outcomes where there is a unique winner. So a preference profile with a unique winner, and then one voter lies about his or her preference relation such that the new winner is different from the original one and is preferred to the original one by this particular voter. So that's an example of strategic manipulation. So we have seen that this is already violated, or that 2 rules, borders rule and plurality, can be manipulated. And I already mentioned before the break, I think, that there's a quite striking impossibility result. And this is the Gibbard-Satterthwaite impossibility theorem, which was already proved in the 70s, but uses extremely mild conditions. So we are going to show this formally later in this course, and basically shows that all rules can be strategically manipulated. So in particular, all the ones that I showed you today, all of them can be manipulated. If you have only 2 alternatives, again, things are fine. So you can do majority vote between these 2 alternatives, and there's no way how you can manipulate this. But if you have more than 2 alternatives, then basically every voting rule can be manipulated. Okay, so here there are some follow-up questions concerning tie-breaking, how to compare sets. So I briefly mentioned this, or we can have probability distributions that select winners. A particular problem in computational social choice is that has been studied for many years, is that maybe in some cases, so we know that every rule can be strategically manipulated, but maybe computing a beneficial manipulation is difficult. So in the border example, it was pretty simple. So you need to figure out how to lie about your preferences in order to get a better outcome. But there are some rules for which it is difficult in the sense of NP-hardness to find a beneficial manipulation. So here then NP-hardness can be used as a shield against manipulation, because you can manipulate in principle, but it's a computationally hard problem figuring this out. So this approach has some drawbacks, however. We are going to talk about this later in the course. You can also look at restricted domains of preferences, for instance, if you have only 2 alternatives, or if there are other certain restrictions on the preferences, and in these cases you can have rules which cannot be manipulated. So I'm speeding up a bit because I also want to show you this example, which is an example of strategic abstention. So this can be seen almost, it's not strictly speaking a special case of manipulation, but it's quite related to that. So the idea for strategic abstention is you get a better outcome by not taking part in the election, by abstaining. Okay, so we can, like, if all of us are going to vote about something, then the winning alternative is A. Okay, I'm not satisfied with this alternative, and then I decide not to take part in the election. Then all of you vote, and then this suddenly results in alternative B, which I like better than A. So that should not be the case. So it should not be the case that I can get a better outcome by abstaining from an election. But even this is possible under quite reasonable voting rules. So here, I'll leave it to you to figure out the details here, because it's another simple example. So you can have plurality with runoff, so the French election system here. And then it turns out that alternative A wins. But if any voter from the last column here, so there are 3 voters like this, if they are abstaining, so if you have a preference profile that rather than having 8 voters only has 7 voters, so one of the last column abstains from the election, then alternative B wins. And this is actually better for those people here. Okay, so these people have alternative A as the winner, One of them decides, okay, no, I don't like A, so I don't go to the election next time, and then maybe the same preferences are used. And then suddenly candidate B wins, so that means a voter is better off by not taking part in an election. And this is, of course, not something that you would want to have. And it turns out, so here again is the semi-formal definition. And it turns out that out of the rules that we have studied, plurality and borders rule cannot be manipulated by strategic abstention. So there you are always weakly better off by participating. It's never the case that you are better off by not participating. But these are basically the only rules for which this is the case. So scoring rules in general have this property, but virtually all of the other rules, so there are some minor additional conditions here, violate this property. In particular, all of the other rules that we have studied in today's lecture. All right. So since I started exactly on time, I would also like to finish exactly on time, because this is something I've never achieved in the first lecture. So this is the very last slide. So I have like a minute left or something. So because it's always good to have this as the last slide, because I could talk for this slide for as much time as there is left. So today it will be a bit quicker. But basically this information is also on the website already. So this is an overview of what we are still doing in this course. So this is the first lecture. This is what we have done today. Next lecture, we are going to talk about choice theory for a single decision maker. We are going to formally define rationality, consistency, rationalizing relations, things like these. Then we move on to social choice. And this is where we are going to see May's theorem. May characterizes majority rule as the best voting rule for two alternatives using a certain set of convincing axioms. So as I said, for two alternatives, everything works fine. Then we have the good news, and then we move on to more than two alternatives, and then the bad news starts, because there's Arrow's impossibility and lots of variations of Arrow's theorem, which has brought the reputation to social choice that social choice is in the science of the impossible, because there are so many papers that only prove negative results. So in this course, we will view it from a slightly different angle. So we will talk about these results in one lecture, but then we'll move on and see how we can get positive results by changing the underlying assumptions. Okay, so and then for the rest of the course, we will define different kinds of social choice functions, like scoring rules or functions that pick the Condorcet winner. For some of them, we will see complete characterizations. And as I mentioned earlier, in the end, we will move to strategic manipulation and see this Gilbert-Satterthwaite impossibility theorem, and also talk about randomized rules. So that's the basic outline for the rest of the course. Yeah, I hope I showed you something today that you like. And if that's the case, I will probably see you next week. Thanks for your attention, and see you next.